Okay, folks, we can get started. How's Lab 3 treating people? I've seen at least 2 or 3 working motor control boards. Did anyone have any luck over the weekend getting one put together? Okay, so let me just remind you where we were. So last time, well, I guess time before last time, because last time we talked about final project ideas. Let me just remind you that what we had been talking through was the motor control circuit that you all are implementing in lab this week. And in particular, what we talked about is the motor as a noise source. So in order to understand the nature of the noise that we must protect our microcontroller against, we first have to understand the actual mechanisms by which these motors make noise. So we had a conversation about that. And then through that conversation, we incrementally built up and justified sort of all of the constituent components of this circuit. So let me just briefly remind you that we talked through the necessity of this snubber diode because that motor has quite a large inductance in it. And when we turn the current on and off through that motor, because of the large LDIDT associated with that inductor, we should expect very large spikes in voltage of opposite polarity. And so we need to provide a safe path to ground for that opposite polarity voltage, and hence the snubber diode there. We talked about the necessity for this bypass capacitor because of the large amount of very high frequency noise generated by the commutator. I'm going to invite all of you to take a look at this in lab this week. It's a pretty interesting experiment to set up one of the scope probes. Don't connect it to anything, so just leave it dangling, and put the scope into FFT mode. I was playing around with this over the weekend. When you do that, you see a few interesting things. One of the things that you see is a big old spike at 60 hertz. Why? Exactly, yeah. All the wires in the walls, the 110 volts at 60 hertz, you'll see that on the scope in FFT mode. But what I'll invite you to do is put it in FFT mode and turn on the motor, and what you'll observe is at all frequencies there's an elevation in noise. A lot of that's coming from the commutator. That's what we're trying to protect the microcontroller against. So we talked through that. We talked through the necessity for this power MOSFET that we're using to actually pulse width modulate the high current motor. And then the necessity of the 4N35 optical isolator to fully electrically isolate our microcontroller and sensors from our motor, right? So I'll just remind you that this 4N35, it's a single integrated circuit, but inside of that integrated circuit, there's a little LED and there's a little phototransistor. And that means that we can control this circuit from this circuit with photons instead of electrons. So there is no electrical connection between these two circuits. The one is fully electrically isolated from the other. Now, some of the things I just wanted to remind you about is in order to maintain that electrical isolation, it affects our debugging workflow a little bit. So let me just remind you that you are definitely going to want to use the scope to observe the signals that are happening over here, and in all likelihood to observe the signals that are happening over here. Keep in mind that the scope's to ground connection on those probes are internally shorted. And so if you have one scope probe connected to this side of the circuit attached to ground, and the other scope probe is attached to this side of the circuit attached to ground, you've connected these two grounds, and you no longer have electrical isolation. So just be cautious, okay? Observe one side and then the other side. Now, the other thing that I wanted to just remind you of is when you get this circuit built in lab, please do not build the whole thing and then test it. As some of you have discovered, that it won't work, right? So we want to test it as we go. I advise that you build this part of the circuit first, the 4N35 and its associated current limiting resistor here, and then the bandwidth setting resistor here. Set this up. Drive it not from the RP2040, but instead from a function generator. And there's a few things that you can take that you can test for here. The first is you can probe the input pin to the LED there and microcontroller ground. And what you should observe if you're properly turning on that LED is the diode drop across the LED. You can measure that. And that should give you confidence that, okay, we are indeed turning on the LED inside the optical isolator. Then, once you've confirmed that, you can probe the opposite side of the circuit right above that BJT there. And what you should see is precisely the PWM signal that you're sending in inverted, right? Because this is a low side switch. Keep in mind, the function generators in the lab, they do not tell you on their little screens what voltage they're putting out. And if you take a look at those function generators, they can make a lot of voltage. So before you plug anything into your circuit, the first thing that you'll do is take your function generator and attach it directly to the scope. Make sure that it's generating 0 to 3.3 volts at a kilohertz. Use the scope to confirm that, and then interface it with the rest of this. Any questions about that? Any gotchas so far that people have bumped into? This seems to be going relatively smoothly for folks. I'll just remind you, this 5 volt, I'll invite you to use one of our AC adapters in the lab, the little wall warts. They can push just a little bit more current, which gives our motor a little bit more oomph. Okay, so when you come to that, just let me know, and I can show you where that stuff lives. Any questions about this circuit before I move on? By the way, what I'd like to talk about today is the PWM, the pulse width modulation peripheral on the RP2040 that we'll be using to control this whole thing. Before I do that, though, we have to say goodbye to Lab 2. But before I do, I have just a couple more things I want to mention about it, because at the end of the week last week, there were a couple of bugs in Lab that were just amazing, just delightful. One of the bugs that I just want to talk through, because I hadn't anticipated it, and it was really interesting. There were a couple of groups in the class that so optimized their Galton board animation code that they were not time limited in the number of balls that they were animating, but instead they were memory constrained. So that is to say, they had 4,000, 5,000, 6,000 balls bouncing through this Galton board, making a distribution here at the bottom. And they were doing that at 30 frames per second, and in fact, they had some time to spare. And so if only they could store some more ball state in memory, they could, in fact, animate more balls going through the Galton board. And we talked about how this might become a constraint that you bump into, and in the event that you do bump into that constraint, there's two latent sources of potential memory that you may tap into. One of those latent sources that we mentioned is the VGA driver. Unmodified, the VGA driver uses 4-bit color. So for every pixel on the 640 by 480 screen, that's 307,200 pixels, there's 4 bits to specify the color of that pixel. 1 for red, 2 for green, 1 for blue, right? We don't really need that much color resolution, and so one of the suggestions that I offered is, well, you could modify that driver to 1-bit color, and you'll get yourself back like 3/4 of the memory associated with that, that VGA driver, right? That's a slightly challenging modification, and most folks ran out of time. There were some folks that attempted this, but ran out of time. But the other modification that I suggested was, at present, many of you were using 32-bit fixed point values to hold your ball state. Not floating point, because it was too slow. You were all using fixed point. But you were using 32 fixed point values. And in particular, many of you were using 16.15 fixed point. That is to say, 16 integer bits and 15 fractional bits. So if you're using such a value to hold your state for ball's position and velocity, that suggests that essentially, to hold the position and velocity for each ball, that consumes 32 times 4 bits, right? Some folks made the clever observation that, well, maybe we don't need that many bits, right? Maybe we can sacrifice a little bit of that fractional resolution, and the physics will all look just fine. And indeed it does, but it leads to a really interesting symptom. So there were a couple of groups that said, all right, we're not going to use 32-bit fixed point. We're going to drop this to 16. So instead of using 16.15 fixed point, they said, no, we're going to use less. And many groups used, what, 5.11 or so? For position, you need at least 10 fractional bits in order to hold numbers as big as 640, width of the screen, right? But they dropped this. Physics looks just fine. Let me tell you the symptom. Groups for whom this occurred, just stay quiet for a moment. Let me tell you the symptom and see if you can tell me what the reason was. Drop some balls through the Galton board. Physics all looks great. They're bouncing through just fine. But the distribution that forms at the bottom does not look Gaussian. It looks lumpy and strange. Physics all seems fine, but the distribution does not look good. Why might this be? Let's look at that statistics of the Galton board page. Let me just remind you of this. This is so interesting. Let me just remind you that what that distribution at the bottom is showing us is essentially, you guys are doing 16-row Galton boards, it's essentially a visual representation of the number of paths that a ball might take to each of those bins. And remember, rather delightfully for a Galton board, for an idealized Galton board, those numbers of paths are represented by the binomial coefficients, which can be represented by Pascal's triangle, right? And so it's very easy to figure out, all right, for a certain size Galton board, you know, how many paths are there to each of these bins? You guys were doing a 16-row Galton board. Let's see, 16-row Pascal's triangle. That suggests a lot of paths, right? And in fact, it's sort of 17 rows, because the 17th row is the bin. But all I just want to point out is that to your center peg in your bottom row, there are almost 13,000 paths to that particular bin. In order for our distribution to show up down here, what we're really doing is kind of sampling, randomly sampling all these paths, and what ends up forming is this distribution. But if we don't sample enough of those paths, then of course the statistics don't start to emerge. And so why could this lead to a strange symptom where the Gaussian does not emerge? The reason is, unless you changed anything about the physics, the only source of randomness in our simulation is the initial conditions, in particular, the initial x velocity. And many of you were initializing your x velocities to some fixed point value in the range of -1 to 1 pixel per frame, which in this representation meant the number of possible velocities was something like 2 to the 16th, quite a large number. In this representation, the number of possible velocities was 2 to the 6th. It's like 64 or something, which is not enough, and so you don't end up with this distribution forming. I can think of two solutions to this. And in fact, the groups tried these two different solutions, and they seem to work okay. How might you mitigate this? Yes? Yes, you could. So every time the ball hits a peg, you could randomize it a little bit, which is actually kind of physical too, right? You could think about this as, well, perhaps we're modeling a little bit of imperfection in the balls or something like that. And so they bounce a little bit randomly every time. The consequence being that you have the opportunity to explore more of these possible paths. How about another solution? Aiden?
You can find more fractional bit velocity.
Yes. You could use two different fixed point representations to hold the two different kinds of state. One for position, where you have enough integer bits to keep track of the number of pixels on the screen. But you could make the observation that our velocity is not going to exceed, what, maybe 10 pixels per frame or so? We don't need this many integer bits to hold velocity. So why don't we shift our decimal point up? We'll have less integer bits for velocity and more fractional bits. This requires a little bit of extra footwork, because if when you're doing arithmetic between two fixed point values, like we talked about in a previous lecture, we need to be cautious about multiply. We need to rewrite how multiply is conducted, likewise with division. But previously we had stated that addition and subtraction just work, because it's just 2's complement addition and 2's complement subtraction. That no longer holds when your two fixed point values are not of the same type. And so it requires rewriting the addition and the subtraction routines in order to make sure that what comes out is a properly formatted fixed point variable. Just too delightful not to talk about. The other bug that I wanted to mention, and I want to mention this one because it leads it's a nice segue into a topic for today, is there were a handful of groups that interfaced their potentiometer with the RP2040, and they noticed a lot of noise on the analog input. Now, some of that noise is certainly expected, right? We talked in the ADC lecture about how we have a 12-bit ADC, but the effective number of bits is 8.7. which means we should anticipate and expect some noise in the lower bits of that ADC. But there were some groups that were seeing a lot more than might be expected. So as always, we scope right at the input to the GPIO to see what that signal looks like. And what we were seeing was a lot of noise at 60 hertz. I just mentioned this at the beginning of the lecture. Where is the 60 hertz coming from? I already told you, it's from the walls, right? It's the 110 volts, 60 hertz AC current in all the walls. This is what you're observing there is your wire connecting your potentiometer to the microcontroller behaving as an antenna. Now, I've reinforced throughout this entire semester that what makes this class so interesting is that physics is a part of your debugging environment. You can have perfectly executed code, you can have a perfect schematic, but physics can intervene. And so you need to be conscious of how you are doing physical layout of your system because physics will intervene on what you're doing. In this case, this particular group had a long dangly wire connecting the potentiometer to the input pin. We moved that potentiometer right up next to the input pin, shortening the wire, 60 hertz noise effectively disappeared. And so the thought that I want to just put in the back of your consciousness moving into today's topics is your wires act like antennas. What we were observing in that particular bug is that it's receiving ambient electromagnetic activity. What I want to talk about today is in addition to receiving stuff that's happening electromagnetically around it, your wires can also transmit power to wires around them. And we need to be cognizant of that, particularly in Lab 3. Because we have some sensitive sensing going on, and we also have some high-speed digital motor control going on. One can interfere with the other if we're not careful. And time permitting, I want to show you a demo of this, but we'll see if we get to it. So, okay, any questions about any of this? The next thing I want to talk about is pulse width modulation on the RP2040. Pulse width modulation as a principle is something I'm sure you're all familiar with, but I want to talk about this specific peripheral on this specific board. There's some vocabulary that's unique to it that we should go over. Okay, that being the case, then let's approach this like we always do. I want to start in the data sheet so that we can gain a familiarity with the hardware that we're going to be controlling by way of the software, and then we'll look at some demo software, and because of our understanding of the hardware, we'll have a better understanding of how that software works. So let's scroll down. Actually, before we even look at that, let me just show you a picture that we've been returning to many times throughout the semester. It's nice to revisit this after every lab. This, I'll just remind you, is a high-level block diagram of all the stuff in the RP2040. We've been going through this stuff throughout this class. And I wanted to just show this to you to hopefully make you realize how much of this stuff you've already been exposed to, right? So we've seen, for instance, SPI. That's how we communicated with the DAC in Lab 1. We've used the UART channel. We used the ADC in Lab 2. You were all exposed to the PIO peripherals by way of the VGA driver in Lab 2, and indeed many of you modified it. We've been exposed to the DMA channels by way of that, the sound effect production. You all had to modify the DMA channels. You've all, of course, been exposed to memory. Some of you have been exposed to the constraints imposed by these memory, by the amount of memory that we've had. You've all been exposed to both processors because many of you chose to do a multi-core optimization for your Galton board. And many of you also have played a little bit with the PLLs because you overclocked in order to get more balls going through your Galton board. So we've seen a lot of this stuff. Some of the stuff that we have not yet seen and that we will visit now in Lab 3 is the PWM peripheral. This is how we're going to be controlling the motor. And the I2C channel. The sensor, the IMU, the accelerometer and gyro that you will be using to estimate arm angle is an I2C sensor. Chose this sensor for a number of reasons. One of the reasons I chose it is it allows for us to talk about I2C. Okay. So we've seen a lot of this stuff, and you're going to get exposed to some more of it in this lab. But let's take a look at the PWM peripheral. And you will be delighted to learn that as compared to the PIO that we spent the last 2 or so weeks talking about, which by the way is all of chapter 3 here, PWM is, oh, look at that. It's only like this big. So compared to what the last peripheral we talked about, this one's relatively simple. Okay, so let's take a look at it. Some of the features of PWM on the RP2040, you can send a PWM signal to any one of the GPIO outputs on the RP2040. So you could have 30 PWMs going out. That's a lot of motors, right? So you can send a PWM to any GPIO, but you do not have total freedom with all of those channels are not fully unique. So the way that this peripheral is organized is it's organized into 8 PWM slices. This is the vocabulary that the datasheet uses. I'm not sure why. 8 PWM slices. Each of those PWM slices is totally independent. So what that means is for each PWM slice, you can specify a unique period for that PWM wave and a unique duty cycle for that PWM wave. Totally unique, 8 of them. Each of those PWM slices has 2 outputs that map to, well, for now, let's say they map to 2 GPIOs. So for instance, GPIO 0 can be mapped to PWM slice 0 output A. GPIO 1 can be mapped to PWM slice 0 output B. These 2 outputs attached to the same PWM slice might have different duty cycles. You can independently control their duty cycles, but they will have the same period. We're going to look in just a moment at the registers that control these slices. Each output has an independent register associated with its counter compare level that sets its duty cycle, but they share the register that sets the period. So what this table is showing us is for every GPIO, which PWM slice does it map to, and which of those 2 outputs does it map to. So 0 and 1 go to slice 0A, slice 0B. By the way, this organization of the PWM is kind of handy for our purposes for this lab. We aren't really making use of the fact that we have these sort of slice arrangement here, where this kind of organization is really handy, where you have a single slice that shares a period, that is to say they're perfectly in phase, but with independently manipulable duty cycles, is for controlling like H-bridges and stuff. In a previous lab, we were doing an inverted pendulum. We were controlling motor 2 directions. It's really handy, actually, to have these 2 outputs attached to the same slice. So in any case, this shows us that GPIO 0 through 15 here map to slices 0 through 7, A and B. And then this repeats. GPIOs 16 up to 29. GPIO 16 is also connected to slice 0 output A. GPIO 17 is also connected, like GPIO 1, to slice 0 output B. What that means is if you're setting up PWM slice 0 and you're setting up the output A channel, you can map that output to either GPIO 0 or GPIO 16 or both. And if you map it to both, then identical PWM signals will come out of both of those GPIOs. That's worth knowing, perhaps for some of your final projects. It could be handy. Perhaps, for instance, you want to send identical control inputs to 2 motors. That's a really handy way to do that. Or possibly, perhaps you're building some robot and the physical construction of the robot makes it challenging to access and probe, say, GPIO 0, which is on the left side of the Pico, viewed from above. But perhaps the way that you've built it, GPIO 16 is more accessible. You could send the same output to both GPIOs, they don't care, and just leave one hooked up to the scope so that you can make your system more observable. In this lab, you could, for instance, send one slice for a particular slice and a particular output. You could send one GPIO into the motor that we're actually controlling. You could send the other one into a hardware RC filter, a low-pass filter, and scope it. And on the scope, you'd be able to observe in real time the output of your PID controller. You'll be asked to make that visible on the VGA screen by way of a digital low-pass filter. But you could do it in analog and put it on the scope as well. Actually, I'm going to have folks do that next year. That's a good idea. Okay. Okay. So 8 PWM slices, each slice maps to 2 outputs, and there are 2 GPIOs associated with each output. Each output on a particular slice can have an independent duty cycle, but they share a period. Let me just remind you how these PWM peripherals generally work. This one, it turns out, you can set up in a couple of different ways, but this is sort of the canonical organization of a PWM peripheral. It is composed of an incrementing timer that is counting up to some value labeled on this diagram as top. Top is the name of the register here that specifies how high that timer counts. So you could imagine that by changing the value of top, what we're changing is the period, the frequency of this PWM wave. The other degree of freedom that we have here in order to adjust the frequency of the PWM wave is each PWM slice also has a clock divider. So we can slow down the rate at which that timer counts up to top relative to the system clock. But it can count as fast as the system clock, 125 megahertz. As that timer counts, it is always comparing its value against the value in a separate register called the counter compare level, the counter compare register. In the event that the timer's value is less than the value in the counter compare register, then the output of the PWM channel is high. As soon as the value of the timer exceeds that level, it goes low. So you can imagine that these two are going into a comparator, right? We're comparing these two levels. For as long as counter compare is greater than the timer, output's high. As soon as that switches, the comparator toggles and the output goes low. So these are our degrees of freedom. By manipulating the value in that counter compare level register, we're affecting the duty cycle of this PWM wave. That's what your PID controller will be changing. By changing the value of top, or by adjusting the clock divider, we can affect the frequency of this thing. Does that make sense? Any questions about this? Okay. There's some other kind of interesting features of this particular PWM peripheral that are perhaps worth knowing. You can configure the timer associated with the RP2040's PWM peripheral such that instead of counting up and overflowing and counting up again, it instead counts up and then counts down, and then counts up and then counts down. But it'll keep doing that comparator comparison between the timer value and the counter compare level value. So this halves our output frequency, but it gives the PWM output the property that the center of our high pulse is always exactly centered at when the timer hits 0. Does that make sense? So what this suggests is we can change the duty cycle, and no matter how we change the duty cycle, the phase of the PWM output is not affected. It always stays centered right there. It might grow and shrink, but it stays centered right there. And so if you're generating two PWM outputs and you care deeply for your application about the relative phase between those two outputs, this allows for you to enforce that those phases never change, even as you change duty cycle. For our purposes for Lab 3, we don't really care about this. For some of your final projects, you might, depending on what you're doing. Wanted to mention just a couple other things about this before we look at some code. These two registers that we generally use to manipulate the frequency of the PWM and the duty cycle of the PWM, the top register and the counter compare level register, they're double buffered, which is really handy. So what that means is asynchronously at any point you can go in and adjust the counter compare level register, changing the duty cycle, and that change will take effect on the next falling edge of your PWM output so that you don't get any glitches on your PWM output. You can imagine that if this was not double buffered, this is what this diagram is showing us, right? And we were generating a PWM output with the counter compare at some level, and then we raised it. If it were not double buffered, we would see this glitch here because the comparator would toggle in one direction again, and then we would get to our new level and it would toggle again, and we get this glitchy output. Instead, those are double buffered, which means you can change it at any old time that you want, and you can be assured that there will be no glitch on your PWM output. The frequency or the duty cycle will change on a falling edge. For sensitive applications, that's really, really handy. Okay. Clock divider, of course, you can turn down the speed with which the PWM timer ticks relative to the system clock, subject, as always, to some limitations. You can slow it down by a factor of as much as 256. So you can slow down the clock by a factor of 256, but no greater. And we'll have to actually in this lab because we're generating a kilohertz PWM signal, which is quite slow relative to the 125 megahertz system clock. Okay. And then last, just interesting thing that I'll mention, because this might actually be quite relevant to some of your final projects. This PWM peripheral on the RP2040 has a really cool feature, which is the B channel for every slice, you can toggle to an input. And instead of specifying a duty cycle or a frequency of some square wave, you can send a square wave into it and use it to measure frequency or duty cycle. That's worth knowing because there's a whole family of sensors where that encode the information that they're communicating in the duty cycle or the frequency of some PWM channel, right? This allows for us to very easily integrate with such sensors. Okay, any questions about the hardware before we take a look at some software for controlling and manipulating this hardware? Again, conceptually, I imagine that this is all quite familiar to folks, but there's some unique stuff to the RP2040 that's worth talking about here. Okay, so let's look at some code. And the code in particular that I want to look at is the demo code for this week in lab. So we're going to take a look at the PWM directory, the PWM demo here. This is the code that you will all be starting from in lab. There's not a lot going on here, okay? I'll just mention, we'll look at this in detail, but all that this program does is prompt the user for a number that represents a duty cycle, and it's generating a PWM output. You specify some new duty cycle, and the new duty cycle takes effect, right? So you could scope the output here. You're going to see some square wave. Say, give me a 90% duty cycle, and the duty cycle goes to 90%, okay? It's a starting point. Like I said, there's not a lot going on here. We see some familiar includes up top. The only new thing here that we may have not seen before is the hardware interface library to the PWM peripheral. Okay, so we've included that. We see some macros here. Their names suggest how they're used, but we'll see how they're used also in a moment. The wrap value here, we're going to use this to specify the value in that top register, the one that specifies how high the PWM counter should count before it overflows. We're going to have it count up to the number 5,000. Our clock divider, which we'll use to slow down the PWM peripheral's clock relative to the system clock, is set to 25. So those two numbers specify the frequency of our PWM output. What frequency are we generating with these two numbers? Well, let's see. Our system clock is running at 125 megahertz. 1, 2, 3, 4, 5, 6. We've clock divided that down by 25. So our PWM clock is only ticking once every 25 system ticks. So that means our PWM clock is ticking at 5 megahertz. And it's going to overflow. That is to say it's going to generate one period every 5,000 of those ticks. 1 kilohertz. So this is going to generate a 1 kilohertz PWM output. Now you could imagine we could generate a 1 kilohertz output with some different values for the wrap value here in the clock divider, right? You could make the clock divider a little bit greater, which is to say the PWM is ticking more slowly, and drop your top value. You could also get a PWM output. What you're sacrificing there is the resolution with which you can dither the duty cycle. Okay? But keep in mind your constraint here. You have two constraints. One is your clock divider may not exceed 256, the biggest that can be. Your wrap value, the value in that top register, is only 16 bits wide. Turns out, though, that you can generate a pretty darn slow PWM wave, even subject to those two constraints, slower than we care to. Slow enough to drive a little servo motor, which many of you know takes, what, a 50 hertz PWM? You could do that with this. Okay. And then all that's going on in this program is we have an interrupt service routine, which we'll take a look at in just a moment. We have a single thread prompting for user input. But let's start by jumping down to main. Call stdio init all to set up a UART channel. Okay? And then here is our PWM setup. The first thing that we're doing is we're specifying that the GPIO that we've named PWM out, GPIO 4, is going to be controlled by the PWM peripheral. This is very analogous to like in Lab 1 when we set up our GPIOs for the SPI channel. We have to tell that GPIO, hey, you are going to be controlled by the SPI peripheral, or you're going to be controlled by the SIO, or by the I2C. We're telling GPIO 4 here, you're going to be controlled by the PWM peripheral. We then need to figure out which slice, which PWM slice is GPIO 4, the PWM out GPIO, connected to. Now that we could absolutely go to the data sheet here. We could go to this table. We could go to this table and we could say, oh, GPIO 4, that is output channel A of slice 2. The SDK just allows for us to be a little bit lazy. This particular SDK function says, please just give me whatever slice that particular GPIO happens to be attached to. Okay, it's going to return 4. We know that, but that allows for us to be a little bit lazy. Okay, then we're setting up an interrupt service routine associated with this PWM channel. We're going to fire this interrupt every period of the PWM. So just like in Lab 1, when we were setting up an interrupt associated with the timer peripheral, you may remember that in order to set that up, we had to tell the peripheral, please turn on interrupts. And then we had to go to our ARM processors and say, you too, please turn on the interrupts, and we connect the two. Likewise here, our first step is to go to the PWM peripheral and tell that peripheral, hey, I would like for you to turn on your interrupt associated with this slice. So we're saying, please clear that slice's interrupt, and then please enable PWM interrupts associated with that slice. True means turn it on. So that is us telling the peripheral, turn on interrupts for that slice. We now have to go to the ARM and say, hey, I'd like for you to listen for interrupts coming from the PWM peripheral. We do that by way of the interrupt hardware support library, right, where we're saying, please enable the PWM interrupt wrap peripheral. Oh, and every time it fires, please call this function, which we'll take a look at in just a moment, but this is going to be our interrupt service routine. And then we enable it. So I'll just remind you very briefly that PWM interrupt wrap, that comes from, if we take a look at the SIO here, that comes from our table of 26 interrupts, right? One of them is associated with the PWM channel. So that's the one that we're turning on. Sorry. Okay. Now, we are setting those two registers that specify the PWM channels, period. In particular, we're setting the top register, the register named top, the value to which the counter counts. We're setting it to wrap value, 5,000. And we're setting the clock divider for this particular slice to 25. So now that PWM channel, that slice, is configured for 1 kilohertz output. Then we specify some duty cycle here. So this is us saying, please set the counter compare register for PWM channel output A of this slice to 3,125, just some number. This is the number that we're going to prompt the user for that you can just change, right? But I just want you to notice that when we're setting the wrap value in the clock divider for this slice, there is no argument to specify the output channel, because like I mentioned, the two output channels of each slice have the same period. So they share a top register and they share a clock divider register. But this one, which specifies the value of the counter compare register for the output channels, asks as an argument for the channel, because we can independently manipulate those two duty cycles. And as always, if we cared to, we could dive down into the SDK. All that this is actually doing is going down and touching some of the registers that we could go look up in the data sheet. And you could do all this configuration by doing that low-level register manipulation. This is just making it a little bit more human readable. Okay? All that this is doing is abstracting register manipulations. Okay? And then we turn it on. And now it's running, and we start the serial thread. We can look at that thread in a moment, but let me just pop up here to the interrupt service routine. So what's this interrupt service routine doing? All that it does is clear the interrupt that brought us here. Right? It's our responsibility as the programmer to clear the interrupt once it fires. And then we're comparing the value of two variables, one called control, the other called old control. In the event that they don't match, then we set old control equal to control, and then we set the PWM duty cycle to that value control. As you could probably imagine, all that we're prompting for in the serial thread here is for the user to give us some number on control. Every time it changes, we adjust the duty cycle. Okay. So we're adjusting the duty cycle every time this interrupt fires, if it changes. It'll fire on after every period, that is to say on falling edges of the output. But I just said these were double buffered. Do we really have to do this in an interrupt? Couldn't we just do these adjustments totally asynchronously, and the double buffering means that that just takes effect? Yes, absolutely. This is me just being a little bit kind, because you will require your PID controller to run at a kilohertz. Rather than using the timer peripheral, like in Lab 1, to set up that 1 kilohertz interrupt, this allows for us to use the PWM channel to do that interrupt. Okay, so this is setting up a little bit of infrastructure into which you will insert your PID controller. What do people think about this? So in this lab, like in all your labs, you have multiple processes occurring at the same time. Some of those processes, and they're occurring at different rates, and they are of different levels of priority. In Lab 1, you had a high-speed, high-priority process in your audio synthesis. You had to send new voltages to the DAC 50,000 times a second, or else it didn't sound right. And so because that was a high-priority process, that went into our interrupt service routines so that we could guarantee that that process would execute at the rate that we specify, regardless of what may be occurring in our application code down in our threads. In this lab, we have a similar high-priority process. The high-priority process in this lab is your PID controller. Like we talked about when we introduced this lab, this system is not controllable unless your controller is running at about a kilohertz. Once it gets above vertical, it's a highly nonlinear system. I've invited all of you to try to control it by hand with the function generator. None of you will be able to do it. You really need a high-speed controller. We enforce the timing on that controller by way of this interrupt. So this is our high-priority process for this lab. Your low-priority process for this lab is going to be the user interface through which you ask for your proportional gain, your integral gain, your derivative gain, and there will also be another lower priority process that is giving you some system diagnostics on the VGA display. You're going to be plotting the output of your controller so that you can diagnose its behavior. You're also going to be plotting the output of a complementary filter, which is estimating arm angle, alongside your desired arm angle so that you can see how well you're doing. But those, compared to the controller, are lower priority processes. Any questions about this? Questions about the PWM peripheral? Questions about the organization of the program that you will develop for Lab 3? Questions about electrical isolation? If there are no questions, I'm going to try a demo that I haven't tried before, which is scary. So what I would like to try to illustrate is just how much noise these high-speed motor control signals can generate. The way that I'm going to try to do this is I have a software-defined radio here that allows for us to observe the spectrum, what's going on at different frequencies on that spectrum. And I want to load up a configuration that I figured out this morning. This is the one. Okay. Okay. It's a radio channel. Hold on. Okay. So there's nothing much going on in the spectrum right now. I have a RP2040 here programmed with a PWM output There's no antenna here. I just have a little jumper plugged in, the same that you'll be using in lab. When I turn this on, look at that. Do you see what's happening? You can see that is the noise generated by just a PWM signal going through this tiny little wire. And in fact, there's so much noise here that, let me put this into AM mode. So now I'm doing AM demodulation. I happen to be turning on and off this PWM channel. I turn it on and off at 400 hertz, which is actually sufficient . The point that I'm trying to make here, all of your wires act like antennas. They will pick up ambient electromagnetic activity. They also generate power that can be picked up by stuff around it. And in fact, this silly little jumper wire that all of you are going to be using in Lab 3, it generates so much power that if you turn it on and off at the right speed, you can send properly formatted AM radio transmissions. By the way, we're listening to like the 8th harmonic here because this doesn't go down to low enough frequencies for me to actually hear it. If we'll see this at every single harmonic of this thing. Look, here it is. And just to illustrate how noisy this is, what we're seeing right next to it is an FM radio station. That's quite a lot of noise, right? And so you will want to be cognizant as you're laying out your project, as you're doing the physical layout of the project, of the proximity of your high-speed digital control signals to your sensitive analog signals. Because this is acting like a little transmitter. The wires connected to your analog circuitry are going to act like little receivers. And what we're showing here is that there's quite a bit of activity that can be picked up by these things. This, just as an aside, wouldn't it be a fun final project to like, it wouldn't take much work to get this to like do the alma mater or something like that. I thought that this would make for a neat like laboratory, a cool diagnostic tool, right? It costs you nothing to do a little PWM channel. It costs you no CPU time. Set up a radio next to it and it would be making different tones based on state that it's in or something like that. Okay. That's all I have time for today. So I will be in lab this afternoon. I'll see many of you there. I'll see the rest of you on Wednesday.